Good morning, everyone. I'm Dendra Best. I'm the Executive Director of WasteWater Education. We are pleased and proud today to host this presentation by Rodney Ruskin of Geoflow. And this is part 1 of 3. They will start at the same time on consecutive days, tomorrow and on Thursday. And this deals with subsurface drip dispersal systems for on-site wastewater. Rodney, I'm getting a little feedback from your microphone, but that may be because I'm on too, but we'll deal with that in a minute here. Okay, this is me. This is where, of course, we do need to let you know that we are seeking funds to do closed captioning for all of our online events. But if you require a text transcript, just email me after the event or when you get the confirmation email, and I will send you a text transcript. As I said, this event is being recorded, and a link will be sent to you after the event. Our legalese here, our disclaimer. Although we present these events as a public service and for education purposes, we just need to remind people that by presenting this particular technology and examples from this particular vendor, it should not be construed that this is an endorsement or an advertisement for this particular technology or this particular vendor. But with that being said, I think when you've listened to the presentation today, you will agree that we should all take a second look at subsurface drip dispersal. And a quick introduction here, and as I referenced before we got started here, all 82 counties in Michigan have been declared a drought disaster area. Almost 2/3 of the country is in exactly the same situation. And I'm sure we've all seen through various professional associations, e-news, and by just participating in other professional events that there is a huge gap between the projected cost of replacing and repairing infrastructure and the amount of money that is actually available. And as a background, again, to the drought considerations that we all have at the moment, the population in the United States has more than doubled in the last 50 years, but our consumption of water has more than tripled. And I know that each of us in our way promotes water conservation, but perhaps our biggest conservation gap is how we treat wastewater. And this is a slide that we like to use a lot. And it's because when people ask what I do for a living, I say that I work for a public education entity that deals with wastewater. And more often than not, they turn their noses up and wrinkle and go, yeah. And I have to say, no, people who are in this profession really are not in the wastewater profession. We're in the clean water business. And we do like this comment by Colin Powell at the back here. So that being said here, I'm going to introduce you to our speaker today, who is Rodney Ruskin from Geoflow. And Rodney is going to take you through a journey on, as a regulator, how do you determine how to assess the site. And with that, Rodney, I'm going to turn my microphone off and turn it over to you.
Good evening, everybody. Welcome. Please, as we go along, submit your questions and comments, and I'll either reply to them immediately, or in the event that I'm coming on to the same topic later on, I will reply to it at the appropriate moment through the presentation. All right, with that, let's get started. I think that when a regulator, as you are looks at a plan that's submitted, there's certain minimum data that's been required for the design. And if the engineer or designer hasn't got that data, then I think we need to ask a question. So let us go through that, what the, these minimum data requirements. Obviously, you need a maximum gallons per day. Not the average, you need the maximum gallons per day. You need the soil loading rate expressed in gallons per day per square foot. Not the maximum loading rate, but the rate that's actually going to be used. You need the variations in flow on a daily or seasonal basis. I mean, obviously, churches get very heavy flows over Sundays or weddings or other events, schools, summer camps, ski resorts, golf courses, vacation homes. In many of these cases, you're going to need flow equalization. In many, many cases, flow equalization is actually a good idea, and on large systems, it's often very necessary. On a lot of single-family homes, it's usually not done because of cost. That's okay. You need to know the depth to the seasonal high water table. If it's present within 5 feet of the installation depth of the drip tube, I should take off my video because there's no point in having it on. Okay. Supply and return manifolds, or the supply and return. So if you're within 5 feet of your drip tube or your supply and return manifolds, which might be deeper than your, which usually are deeper than your drip tube, then you need to know about that. Details of the available area, the property lines, setback from property lines, contours, major 10-foot increments and usually minor and 5-foot increments. Temporary and permanent roads, drives with the minimum setbacks. It's useful to know if often it does happen that there has been a road, not a where there's been compaction, and then the road's been abandoned, and it, it just looks like a normal piece of ground, but in actual fact you have a compacted strip across the prospective field, and sometimes you don't find that until you go in, until the contractor goes in and starts plowing it up. Okay, the location of the pump station, the location of the acceptable drip field flush point. Now that's usually, the flush point is usually back to the treatment plant, but that is not always the case. Utilities above ground and buried, those that are existing and those that might be added in the future. Surface water bodies, okay, obviously. Location and method of crossing, if you're allowed to cross them, streams, dry ditches, drainways, wetland delineation, the location of treatment of the treatment system, minimum setbacks from all structures and facilities associated with collection, treatment and operation. So, okay, you need to know the weather conditions. If you have freezing conditions, if there's rainfall and floods, or if there's lightning. Now with lightning, when you run wires out into the field to operate solenoid valves, if the lightning hits that wire, it's going to travel along the cable and blow out both the valve and very likely blow out the controller. Even though there is usually a fuse at the controller, but boy, if you get a direct hit, the fuse isn't going to save it. So you have to, if you really have a lightning risks, you either have to put all your valves with the controller, excuse me, under lightning protection, or alternative, and run pipes out into the field to the zones, or alternatively, in case the electrical cable in PVC pipe or some other non-conducting pipe, so that it is protected from lightning. System design and layout. You want to know about the absence or protection from flooding. Sometimes the designer has to include drainage ditches around a drain field in order to achieve protection from flooding. Landscape position with a good runoff. You don't want the rain to be soaking into the drain field. Separation to the water table or any other restrictive zone. Obviously, we often have rock and clay layers or other impermeable layers, or layers in which the perk rate is lower than the upper layers. Setback requirements, state and local, and the sufficient end area for the minimum drain field size. If you get a design that comes into you with the minimum, with the minimum drain field size, just happens to exactly fit the area available.
Rodney, Rodney,
yes.
Which microphone are you using, please? Because a lot of people are having trouble with your audio.
Let me just see. I'm using the one on my speaker.
Are you using?
Let me just turn up the volume a bit and see if that helps.
I think it's more that you're cutting in and out.
I don't know why.
Yeah, it's fine here. So.
Is that any better?
Like I said, it's
yes, it's quite correctly. I don't know what I can do. There is another microphone, but I don't know how I can get it connected quickly. No wonder, just let me switch on video. And is that any better? No, not any better. Okay.
Do you have an internal microphone on your computer?
No.
Okay.
I just don't have any adjustment other than the volume.
Okay, I'm getting a message in the chat window that you're not breaking up as bad.
Yes. Well, maybe I should bring this volume up this way and people can bring their volume. Is that any better?
Yeah, it's not a volume issue. I think you're getting some feedback though.
Let me try that. Can you hear me now? Is that any better? Can anybody hear me?
I can.
Is that any better?
But it's not better. Well, some is yes, some is no. So for some people it is. Leslie says she can't hear anything. So Leslie, did you do the audio setup? Okay, I tell you what, I'm going to stop the recording for 1 second here. And Rodney, turn your microphone off, plug it back in, and we'll try again. So okay. Bear with us, we'll give you 1 second here.
Okay, good morning again. As I was talking about a few minutes ago, if the minimum drain field size just happens to exactly fit the area, and particularly if this is a single family home, I would be cautious. Not that, of course, I'm talking of any individual, but people are known to sort of look at the area and then decide that's the minimum, that's the application rate, as opposed to looking at the soil and then deciding the application rate and then coming up with the area. And sometimes, I mean, this is fine. I mean, sometimes it works out okay, and sometimes people have been known to push it a little bit. Generally, well, I'll try moving the microphone a little further. Has that helped? Okay, well, let's continue after that. Well, when one looks at the position for a drain field, obviously the depression at the top there, that's meant to be marking, is out. This upland position here is often dangerous because you might get seepage coming from here across underneath. This upper side slope is an ideal position, the mid slope's an ideal position. If you start getting lower down here, you'll start getting runoff, and you might have to put some diversion around the drain field so that the water coming down gets diverted. And of course the foot slope, the steam terrace and the floodplain are generally not acceptable areas. Okay, and here we've got virtually the same thing, just a picture. So generally you want to be here, up here is the best possible area. Okay, and here we're talking about exactly the same thing. Floodplains, depressions may have high water tables, stream terrace positions may have a high water table. The lower slide slopes and foot slopes, seepage, drainways, surface water, and flooding. Okay. You have to locate your flush and return lines. We recommend that you flush back to the pre-treatment tank. Sometimes we'll flush back to the pump tank. And there are also circumstances on very steep slopes when one might flush down into a tank and then have another pump pumping it back up to the treatment plant. Loop drain field designs are quite popular because that reduces the number of trenches, and you can have the feed and flush manifolds in the same trench. Okay, and this is a fairly typical design. And here you'll have your pump tank, and you'll have a supply manifold going up there and going out into solenoid valves, which will be supplying the two fields. And you notice if this is the slope, I've brought in the supply at the top. The supply at the top, and the flush is taken out at the bottom. So we're supplying at the top, and it's going around, and then when you open this valve, it drains out rapidly through to the bottom. And it's fairly straightforward. I mean, you can use drip line, you can curve the drip line, or you can use blank drip line, or you can use flex PVC. And contractors and designers have their own choices. It's not terribly important. And this is a very, very simple design. Okay. There's a lot of people here from Washington, so because of that, or I understood a lot of people have signed up from Washington, I just will talk a little bit about continuous flush. Continuous flush is not practiced very widely outside the state of Washington. Some people do it, and to be specific, I'd say since about 1985, Clearstream in Texas started doing continuous flush by cracking over the solenoid valve, and they design it themselves, they see to the system themselves, and it works. I mean, so I don't want to say that it doesn't work. There was a detailed discussion in the Wasser pipeline, the winter and spring editions. If you haven't got it and want to read it, contact me and I'll send you copies. The main advantage of continuous flush is lower capital cost. It is a cheaper system. There's one less solenoid, or one less electric valve. There's a simpler controller. It is a cheaper system. And that is the reason people do it, because it's low initial capital cost. However, if you're continuously flushing, you're pumping more water round and round. And that's going to cost considerably more in electricity power consumption. When you look at it, when you pump more water, there is a greater volume of water, so the amount of power consumed is virtually proportional to the volume of water. And then, because you're running at a higher velocity through your drip lines, you're going to have a higher energy loss through friction in the drip line, so that will also increase the electrical power consumption. So in actual fact, your consumer is going to be paying for that lower capital cost with a higher electricity bill through the year. It might be very small, but a few dollars a month, year after year, might come to as much as he saved in the original capital cost. In fact, if it's badly designed, it will come to more than he saved. More frequent pumping of the pump tank, because you've got this water going round and round, and it's going to increase the amount of solids in the pump tank instead of that material going back into the treatment plant to be retreated. So the solids are going to build up more rapidly, and you're going to be disturbing the pump tank with the extra flow of water going around and round, unless you have a settling tank, and then you haven't saved your capital expense. And your filter is going to have a greater load, so there might be more frequent flushing of the filter, which, none of these things cost a lot, but when you add them up, they might be more than the capital cost saving that you've got away with to sell it to the homeowner that you've got a lower price. Energy consumption will be a factor of the flush velocity and the number of laterals, both because the number of laterals will determine the amount of water that's going round and round, and the flush velocity will also determine the amount of water. So obviously, if you're flushing at 2 foot per second, you'll be using considerably more than 4 times the energy of flushing at half a foot a second. Now, often this is a regulatory issue as well. In actual fact, if you're continuously flushing, I'm not sure that you need to flush at a very high velocity at all, because it is continuous, but this is a personal opinion, and I don't think it will meet the regulatory requirements. So in my opinion, continuous flush will reduce capital investment, but the engineer has to be careful to design the system with the minimum continuous flush flow and larger pipe sizes on the supply lines and the manifolds to ensure that the operating expense does not rise excessively. Okay, freezing conditions. If the frost line's greater than 6 inches, you must include manifold drainback in installation of the supply lines, the manifolds and the supply lines and the flush lines. You can bury them deep enough below the frost level. It depends on how cold it is. Your vacuum relief valves are one of the first things to freeze. They must be insulated if you're at risk for freezing. If you're in a really severe freezing conditions, keep your minimum manifold and supply line size to 2 inches, so you can use a steam ice clearing device. Okay, this is just a picture of a typical trench with the manifold and the drip line going out into the drain field. Here we've got your supply lines and your flush lines. We seem to have an extra one, I don't know what it's for. And here we've got the manifold set up that hasn't been installed yet.
Rodney?
Yes. Yeah.
Rodney, a question and a suggestion. Okay, I think somebody just answered there was a question what CAPEX and OPEX stood for on the previous slide, but Lloyd Kemper has, Kemper Lloyd has explained that to you. And on the slide that you're on right now, would you just use your pointed tool and highlight what each part of these are for people who are not familiar with it?
Okay. This is the manifold. We've got one trench and it's going out in both directions. This is a manifold, and here's the drip line. We'll come to this later on and how it's connected. The drip line's connected and going up into the field. And these are supply lines and flush lines going out up to the field. There's an extra one. This is obviously a large job, and it's probably going off into another direction, to another field or another set of fields. Okay, this is a single-family palace in Malibu, and you just don't know where the drain field is. I mean, it's completely under all the grass, and I believe it's gone out to the side and under the roses as well. But one can blend the drain field into the landscape quite easily if the weather conditions are appropriate and if the landscape's appropriate. Okay, how do you set your field sizing? This, of course, is a critical part of the system, is the size of the field. You need to know the quantity of the effluent. You need to know the wastewater strength. Now, in these discussions, I'm only going to be talking about secondary treated effluent. There is no reason not to use drip with primary treated effluent. Less and less primary treated effluent is being used. However, it is perfectly practical if the soil is half reasonable. With primary effluent, the risk is the buildup of an anaerobic zone around the dripper because of lack of oxygen. So again, and with secondary treated effluent, that risk doesn't appear to be there. So with primary effluent, you have that extra factor you've got to look at, which is the risk of an anaerobic zone, which results in a larger area, often a very much larger area, and I would often say more drippers, so that each dripper gets a considerably lower loading of the anaerobic bacteria through the drip system. And again, if you know your soils correctly and it's designed right, it can and does work, but it's one more factor and one more risk that has to be considered. So anyway, as I said, I'm going to consider everything to be secondary treated in today's discussion, or sometimes it's tertiary treated as well. Then, of course, the variability of flow, as we spoke about churches and ski cabins and things like that. The next factor is the soil. The texture, the structure, the depth, the restricted horizons, water table. And soil is the most critical thing, as I'm going to hear me say later on again. You can generally, when there's a mechanical error of some type, you can fix it, whether it's changing a pump or increasing a field size or taking a zone out and putting in another zone. You can generally fix it, but if you've got a basic error in soils, you're in trouble. It's very, very difficult to repair after it's been installed.
Rodney, there is a question from Percy Johnson. What would the minimum depth to a seasonal high water table be?
Okay, I'll talk about that as we go through. Generally, it's a regulatory issue. If you've got secondary treated effluent, the fecal coliform count is usually down to background level within a few inches of the dripper. However, I don't know any regulations that allow you to be a few inches above the seasonable water table. So really it's a regulatory issue. From my point of view, if you've got 18 inches, which is the minimum I usually see, that's just fine. And I mean, and as I said, it varies from state to state, to county, as I'm sure you know. Okay, we've got large versus small systems. Okay, you have to be careful. When drip started, it started with single-family homes. And with single-family homes, you have a very large safety factor because you've got to look at the perimeter to the area, the ratio of the perimeter to the area. With a small system, you're going to get seepage for several feet outside of the area. So your area is actually larger than the area which is covered with drippers. So this is the ratio of the perimeter to the area is a factor. Okay. On a large system, this doesn't apply. And if we go through it, as you can see here, the area here in the black area is much larger, is a high percentage compared to the white area, and as the system gets bigger, the percentage gets smaller. And if you do the arithmetic, taking a 1,200 square foot system, and if it's 100 foot by 12 foot, you're going to come out to adding 4 foot to each dimension. It's 2 foot on each side, 104 by 16 feet. You come up with 18% more disposal area. While if you go to 204 by 10 foot, you come up with 42% more disposal area. And this explains why smaller systems are more forgiving than large systems, and you cannot take the calculations that are published for small systems and apply them for larger systems. It doesn't scale up. And here we took the same thing with 120,000 square foot, and you can see we only ended up with 4% or 3% more dispersal looking at the two. So you've got to bear that in mind. All right, let's go on and talk about what's happening. Now, these pictures are very, very old. The US Department of Agriculture in Fresno did them. Here's a dripper under the ground, and here's a dripper on the ground. And both of them were pulsed. They were not given continuous flow. There was given a short pulse, and then allowed to rest, and the short pulse, and they're allowed to rest. And here we get flow distribution lines here and here, which are here and here. And as you can see, this volume is about 40% larger than this volume. Now, this is perfect Central Valley, California soil. We don't get the soil like this, but the principle still applies. By this pulsing action, we get the much larger volume, wetted volume, so where there isn't water, there's air. And where there's air, we're getting aerobic treatment of the anaerobic bacteria coming through with the effluent. And obviously this will be superior to this, which is more saturated. And when you're pulsing, you allow the capillary action and to move the soil, to move the water sideways and up, as well as gravity plus the capillary action takes it down. And if you look, that distance, sorry I went a little far there, is only a little less than that distance. It is less. And as you can see, that's about in the middle. But now we don't get perfect soil like that, but the principle is the same. We're going to put water in for a short amount of time, maybe about 10 minutes, and allow it to move away from the dripper, allow the anaerobic bacteria to be consumed by the in the aerobic zone, and we're going to get very, very effective water treatment. And furthermore, because we've got this nice wetted area here, which has got air, it's coming through with nitrogen and maybe some phosphorus, we've got some ideal conditions for roots to go into the system, into this area, and the more concentration of roots you get here, that brings in all sorts of insects and soil bacteria and animals that are all favorable to the biological process. So what we've got here is a virtuous cycle. The soil actually has been shown, there was research at Texas A&M, which actually showed the soil improving with time under a subsurface drip system. And this is the heart of why subsurface drip works. I can, yeah. And it's been, as I said, it's been demonstrated as being correct. So, okay, now here we have a typical system. We have a pump tank, and I generally will recommend 4 floats, an emergency off, a activate, a alarm, and a super alarm. And usually when this float comes up, it means that we're going too fast. It means, sorry, we've got too much water, and we will usually program the controller to halve the resting time between cycles to pump it down quickly. And if it doesn't pump it down quickly and this one goes off, then of course all the alarms ring and you know something's gone wrong. Some counties and states don't allow you to do this. Some do, some don't. But it goes from there through a filter. And generally we're talking of either 100 or 130 micron filtration. Okay, this is through the filter and out into the field. Okay, and then it will go through a supply manifold, through the drip line, back to a flush manifold, and back. And in this case, I would like it to go past that into the treatment plant. And here we've got the filter flush. We have a valve here that will open to flush the filter, and this will then flush the filter that way. And so then we've got the cycle. And you've got your 2 valves to operate the system, and you pump on and off in the floats. These are air vacuum relief valves, which are critical because when you switch the system off, it's going to drain. The drip line is full of holes. It's going to drain. And when it drains, you're going to set up a vacuum. And when you set up a vacuum, you can suck dirt back into the system. So you must have air vents correctly placed at the high points in the system. And a minimum of 2 per zone. We don't want to keep the pipe full. There are drippers that keep the pipe full, and I've known people to sell them for this sort of application. It's a very high risk keeping the pipe full. There's 2 reasons I don't like it, and there's 2 reasons it's dangerous. The first one, of course, if it's full and you've got freezing conditions, it will freeze. The second thing, if the pipe's full and you've got bacteria in the pipe, we know that in the secondary treated effluent, there's a fair amount of anaerobic bacteria. When you switch the system off, they've got a lovely, happy breeding ground, and you're going to breed bacteria at a tremendously high speed. And of course, if anybody goes on vacation for a week or 2, they're going to come back and their drip line is going to be filled with bacteria. Okay, what must you look for? The laterals in the same zone should be about equal in length. If you have one lateral much longer and one much shorter, you're going to get your flush velocities are not going to work very well. You know, most of the flush water will go through the short lateral where there's a lower frictional back pressure than through the longer lateral. So they should be approximately equal. I mean, yeah. 10% is just fine. I mean, that's not going to affect it to any great consequence, but sometimes you get triangular fields where people don't think of S-ing the lateral to make, you know, to get 2 or 3 vents to even up the vents of the laterals. You want to hold your laterals on contour. Generally, on small systems, you can do this. Every now and then you come into a very large system where you cannot hold the contour. In that case, there is, well, Geoflow offers one specific dripper, which I'll talk to when we get to the point. But we don't recommend it. Hold contour if at all possible. It's the safest way to go. And when I mean say hold contour, I don't mean with a laser, but within 6 inches or so as you sort of go along. You don't want to be too far off. Okay, flush return. Preferably back to the treatment plant, as I discussed before. You don't want to disturb the pump tank with the effluent going back to the pump tank. And again, if you're not doing it to save money, but just because it's not practical to go back to the treatment plant, which sometimes does happen. Sometimes the treatment plant could be a mile away from the drain field. In that case, I would suggest putting in a settling tank ahead of the pump tank, so that you flush to a settling tank, and then the overflow from the settling tank goes into the pump tank, so that you don't disturb the pump tank. At least 2 air vacuum relief valves per zone, and of course freezing precautions if necessary. Okay, and here you see a field, the beautiful setting, in which they're holding contour pretty well. This is, the drip lines haven't been installed yet, obviously. This is where they're preparing to put in the drip lines. And they've trenched ahead, and they've picked a zone, and I presume that on a slope like this that they'll have several zones going down here, so that when you switch off you don't get a large amount of water flushing down. But I think I can see a separation there. I'm not conversant with this particular detail of the design. Okay, freezing precautions. We have 2 excellent papers on our website. The links are here. Incidentally, if you need the links, as Dendra is saying, she'll be sending them out, but also you're welcome to contact me at any time and or any questions that arise out of this presentation. But those are on our website, and the ones written by Rachel Bora, which was a dissertation on distribution of soil performance in a northern climate, which might be relevant to a lot of the people here. And we've got the whole thesis if you wanted, or just the extracts enough, the summaries enough for most people, but if you're academic enough, you're welcome to read the whole thesis. And this other one's from Scott Wallace, who was with North American wetlands and did a large number of systems up in Wisconsin. And he wrote this paper for us on freezing.
Rodney, one quick message for the participants. All of the content in the chat window can be highlighted, copy and pasted. So I did post the links to all of those documents in the chat window. You can save the entire content, so just highlight the piece that you need, copy it, put it into an email or a text file, and just so that you're not busily trying to write down all those long addresses. Go ahead.
Thank you. Okay, and freezing works, there's no question about it. There's a large number of systems with in freezing conditions. This is one that was installed in 1997 and was monitored. And incidentally, the more snow, as I think is fairly obvious, the better. When you do have problems with freezing, it's when there's no snow and you're not getting the insulation from the snow. Okay. But one of the areas that, one of the most dangerous areas is the air vacuum relief valves. There's water being pushed up here, and it's wet, and it can freeze. And it's one of the most likely areas to freeze. So this needs to be insulated. Here we have a bag with closed cell insulation material in it, wrapped around. Now this is wrapped around so that it is insulated. There's styrofoam insulation around the casing here. Okay, and here they've included a rebar pin so that when it's under snow, when the snow is 4 foot up here, if you do need to find it, you can locate it with from the steel pin. Okay, and this will go down now. Under real tough conditions, which a lot of you have, it's a good idea to put a 5-gallon plastic bucket. This is the container for the air vacuum relief valve, with a valve box with a cover. But underneath that, dig down, put a 5-gallon drum in there and put pea gravel underneath and take this below the freezing. So let's say the soil is frozen down to here, where the soil is frozen, then you'll have warm air, relatively warm air coming up here from the soil. And I know that's extreme, but it works. Okay, and this is Scott Wallace's recommendation, and his systems work.
Rodney, there is a question from Percy asking whether it's recommended for a valve box to be used around those release valves.
Yes, yes, this is a valve box here. Valve box. This is a valve box, and then you've got the top. And you can insulate the top too. There's no insulation on the top, but I would put, if this is the top, obviously put a layer of styrofoam or something under there as well. Does that answer the question? Okay. Drip dispersal systems. Okay. If the supply and flush pipelines are not insulated, you're very likely to get freezing. Okay? You want them to drain. And if they drain, between dosing, they'll freeze in the winter. If they're insulated and below the frost level, of course you'll be okay. But you do have to be careful. It's just as well to have them draining even if they're below the frost level. Okay. There's a very simple technique to achieve drain back, is have a pipe segment with a check valve bypassing the filter on the discharge line. I'll come to a picture showing that in a minute or two. When the pump is off, then the check valve will open and allow the drainage back through the pump. Okay, and as I said, I believe there's a picture of that next. Yes, here we are. And this is the check valve. So that when you're pumping, of course, it's going out this way, and when you switch off, and this is below, the drain field is higher, so that the water pressure flows back here, and then that check valve allows the water to flow around the filter and back through the pump. And then if you don't have that extra check, that extra check, spring check, yes, that allows the water to go that way, then of course it will flow back into the filter and block here, and then the supply line will freeze. So that's a very simple way to get around that without any extra electrical connections.
Rodney, just so I'm clear on what I'm looking at here, would you start at the beginning of this train and just talk us through what we're seeing here?
Okay. All right. Our pump will be here. Our pump will be here, the pump tank here, and it'll be pumping up through when it's normally operating, and then it will come through a filter. This is a simple screen filter shown here, or it could be a disc filter. It will flow through the filter and out to the field. Okay? And then here, coming back from the field, we've got the normal flush back from the field, which comes back here, and this is the field flush valve. Okay? So when you want to drain, you just open this flush valve and there's nothing stopping the flow going back. So simple to drain this flush line. But however, when you switch off, the supply line will not normally drain. It will stay full because without this filter will block it from returning. You've got your pump tank and your pump, and there's no reason that it's going to flow backwards through the filter effectively and drain. So by having this bypass, then this will allow the system to drain, the supply line to drain. I hope that's a little more clear. I mean, you can put in a solenoid valve here too, incidentally. You open the solenoid valve, or you can put in, even better still, an electric valve and open the electric valve, because solenoid valves take some pressure to operate while electric valves don't, which I'll come to in a discussion when we go to a discussion on valves. beware of slow drain back. If you're in extreme conditions, if it takes more than 15 minutes to drain back, the system can freeze. So watch for that. Okay. This is a system design for it to drain. These actually put the drip tubing at a curve. The drip tubing is full of water. I don't think one really needs to offset it to that degree. You've got your valve boxes, and here you've got your slope return to drain back, and here you've got your slope return to drain back. Okay. I think this comment is a little, in my opinion, it's a little unnecessary because, as I said, the drip line's full of holes and it's empty, so if there's a sag, it's not the end of the world. And furthermore, let's take an extreme situation where, let's say the drip line is going like this, and then there shouldn't be, but maybe a gopher went underneath and something like that happens. And this actually does freeze. And you get, in other words, there's a dripper here, and a dripper here, and there's 2 feet of pipe here, and that somehow or other freezes. In actual fact, with this design, you've got your supply line coming up here, and you've got your flush manifold here. So the water, let's say this is frozen here, it's your freezing spot. The water, actual fact, will come in here and stop that way, but water will flow through there to this manifold and back up there. And the same, of course, backing up there. So in actual fact, that frozen spot will be getting comparatively warm water from both sides, and it's not going to stay frozen for very long, and the inefficiency of the system will be absolutely insignificant. But it's better not to deliberately have it sag. Okay. And here is Scott Wallace's technique, where he actually includes a bentonite seal to prevent water from flowing back into the tank. Of course, if this distance is long enough, I don't know anybody other than Scott Wallace that does that. But I'm not opposed to it. Okay, and this is the drip line here, and that is the bentonite seal there. Okay. We'll come to this again, but you do want your drip field to have grass, vegetation, trees. You want to trap as much snow as possible above the drain field to provide insulation. Okay. We've spoken about air vacuum relief valves to sufficient level. We've spoken about insulating them inside and outside, and with the plastic bag. Okay, the valve box with a metal pin we've seen in the picture. Make sure your valve box is big enough to use a wrench and to put in a pressure gauge. Most of these air vacuum relief valves have got Schrader valves on them, and you can put a pressure gauge. So you want to make sure you've got enough space to use a pressure gauge when you're testing it in the field. And again, we spoke about the 2-inch line, so you can put in a strainer. Okay. Pump discharge filter should have a ball valve at the bottom of the housing slightly cracked open. Okay, this means that the filter housing can drain instead of freezing. Again, that's if your filter housing is out in the field and not in the cellar of the house or somewhere that's kept warm, which it sometimes is. Set your field pressures and install a pressure gauge on the return main air vacuum relief valve, which is where I spoke where you have a Schrader valve, and throttle the return main valve to set the pressure. Okay. Okay, I see there's a question there. Are there procedures for preparing the system for winter if home is seasonal and not be occupied during the winter? Yes. I mean, obviously the system's going to drain, and there's not much more you can do than if the system's empty. And what's going to happen, though, is that your treatment plant's going to completely shut down. That's the more critical issue, and you really have to take the necessary steps with your treatment, according to your treatment plant, to get the anaerobic and aerobic digestion working as quickly as possible when you start up, because otherwise you're going to have pretty low quality water coming through, and you certainly will have to sort of flush your pump tank and flush your filters as though you're starting up a new system after the winter. Okay, the first winter, if there's no grass or anything overhead, it's always a good idea to put straw mulch or something over the system. And as we spoke before, landscape the drip fields to trap snow, trees, shrubs, wildflowers, prairie grass, or anything else is adequate for that purpose. Okay, slopes. Okay, we have no limitation on slopes. The regulators have limitation on slopes. But with a drip system, there is no reason whatsoever that you can't tackle any slope. Most of the slopes somehow or other that we work with tend to be wooded, and they're stable just because they're wooded. This is the Mount Tamalpais in just not far from San Francisco, with a 65% slope. Now you have to, on this sort of conditions, you have to install by hand, so that's expensive for labour, but that can't be helped if that's the only possible alternative. But the slope itself is not a limitation. Here again is a system in Yosemite West, where again the system was buried by hand. And there's a link up here if you want to read about designing on slopes. It's written by Mark Carl, designing about slope design, in which he went out to Yosemite West after having been in for several years and wrote a report. Okay, this is not with sewage, with treated sewage. However, it is a subsurface drip system on an incredible slope. And of course, there is erosion control netting. They put down erosion control netting. They had to rappel. The contractors had to rappel on ropes down the hill in order to put the drip lines in across. But they did it, and there's beautiful results. This is in Hawaii. And there's no reason that you can't put in a drip system on a slope. But as I said, you have to be careful. They tied the drip line to the erosion control netting. They put it in and then tied it to the erosion control netting. So as I say, technically, there's no reason. You just have to take precautions.
Rodney, can you go back?
I'd like to talk quickly about reuse.
Yeah, Rodney, can you go back to
Sure.
that previous slide? Mary has a question of the previous slide.
Okay.
There we go. What are the light-colored areas?
You mean these? You're talking about these areas? Mary? Is that
Yes.
Rock. Rock, solid rock. Yeah, here too. These are rock. I don't know how they formed this, but anyway, they did it. I mean, it was obviously done irrespective of expense. But, yeah, if you have enough money and you want the aesthetics, people do things like that. We won't talk about some of the landscaping that's been done by some of the billionaires in Silicon Valley, where they use helicopters to bring mature trees in. People with unlimited money sometimes do spend an enormous amount of money to get the aesthetics they want. All right, let's talk about reuse. Reuse is going to grow everywhere. There's some areas, of course, where the rainfall is so high that planned reuse is just not going to happen, but there's many other areas where even as a supplementary irrigation, as in this particular case in New Zealand, reuse is a major factor in the design of the drip system. This particular system is 1.3 million gallons per day. It was designed by URS. They've written a paper on it. I'm almost sure it's on our website, but I'm not 100% sure. When you do a reuse system, you have to have extra factors involved. If it's either you're going to have the right amount of water to balance evapotranspiration at the maximum rate of evapotranspiration, then during the rest of the time you have to have an alternative disposal field to get rid of the surplus water. Or alternatively, you can design it so that you can use the water at the minimum level, then you have to have makeup water to meet the evapotranspiration needs of the plants. Or you can have a combination of that type of thing. But you have to have, one or the other, and you have to design it and know your soils very, very well and know your plants very, very well. Because there's got to be a cooperative work between the landscape architect and the engineer. And landscape architects are not skilled in soil science for sewage disposal. They may know something about soils for growing plants, but very few of them know anything about soils for sewage disposal. And you're going to have some percolation down. You're going to vary your depth of burial, your spacing of burial according to the needs of the plants. So it becomes very much a cooperative engineering job to do that. The particular engineers at URS have got both landscape engineers and sewage engineers on staff, and of course they can handle this in-house very, very easily. And they've done so on several occasions, incidentally. And as you can see here, they're laying out the drip line, and they're going to smooth it out, and that's going to be, I think, for this area, strictly above us here. But as I said, you're going to get more and more reuse as you progress, as the industry expands and people get more used to it. This again is the same team of people did a golf course at Omaha Beach in New Zealand, and here you can see the line, and the drip field is that way, and this is unirrigated this way. And this is the carry, the tee somewhere over here for those of you who are golfers, and if you can't hit your ball from here to here, you shouldn't be playing golf. You should be at the practice, should be taking lessons somewhere. So that is another very successful, very, very successful system. It started off with 9 holes and it expanded it to 18. And now again on this particular system, excuse me, you can't see it here, but they have a supplementary disposal system somewhere up here on the top of one of these hills, so that if the surplus water, the golf course superintendent can throw a switch and the water can get discharged up to a drain field at the top, on the top of the hill, somewhere up there. Okay, this is Hawaii Kai Golf Course in Hawaii. This is a very old system. I would guess about 15 years old. And they're not allowed, this is a golf course which is being spray irrigated with actually tertiary treated effluent. It's being spray irrigated. I think it meets Title 22 for those of you who are conversant with California's Title 22, but it is tertiary treated effluent. And they're spraying the field. Now you can see, look at the wind. Just look at that tree there. And around the houses, you're not allowed to spray within a certain distance of the houses. So around the houses, they put in drip. And you can see how much greener and better the drip field is than the spray field. And I believe they're both getting the same amount of water, and that, of course, is because of the wind effect. And when it comes to reuse, that wind effect is very important. And okay, and this is another large reuse system. This is Bernardus Lodge in California, in which the entire grounds of the beautiful lodge and very expensive lodge. They've given me a special rate when I've come to see their drip system. But the whole landscape is done with subsurface drip. And being in California with a high summer occupation, they successfully balance the evapotranspiration with the high flows in summer with the high evapotranspiration. High flows in the lodge in summer, which they don't have too many people there when it's raining in winter, so they balance that out successfully without any great amount of supplementary water being applied for the summer. Okay. You're going to see more and more shallow drip mounds. There are drip mounds, you know, as you know, people use drip mounds, where the water table is too high and or where the soil just won't take the water. Now, in actual fact, and again, this is a personal issue, all drip mounds, one way or the other, well, I'll withdraw that. Most drip mounds, one way or the other, are going to break out at the lower level of the mound, because you know water flows downhill. And this was developed by Scott Jones in Washington. He started developing shallow drip mounds, and what he does here, he's got 4 lines, each are 125 foot long. So he's actually taken one roll of 500 foot drip line and he's put in 4 lines 125 foot long. And he's got 6 inches between drippers. The drippers are very close. So he's got 2,000 drippers, 1,000 drippers, 500 feet, 6 inches, 1,000 drippers. He's got 1,000 drippers applying the effluent. Now this photograph is taken before he covered it with more sand. Okay, so you've got a very, very small dose of effluent at each point, and you're getting a very, very uniform application in the sand because water doesn't move sideways by capillary action very effectively in sand, but there's 6 inches between drippers and only has to move 3 inches, which isn't very far. So he's got very, very efficient coverage, and these are monitoring wells. And this is a wetland down below. And these monitoring wells showed completely clear fecal coliforms, clear effluent flowing down into the wetland. Of course, it's not taking up nitrogen or potassium, but it is taking up the fecal coliforms. And of course, the shallow drip mounds are aesthetically far more pleasing than the conventional drip mounds. So this is a technique that I think you're going to see more and more of. We're seeing more of them in Washington. They're getting more popular because that's where Scott started. But I think you're going to see these spreading across the country as the technique gets established. But again, feeding it with drip and with that 6-inch spacing, really get the results in superb quality effluent. And again, if you look at Rachel Bora's dissertation, which we'll come to as we go on later, you'll see why. And if you even go to that slide, remember that slide I started with the USDA showing the way the water moves from a dripper when it's slowly pulsed. Well, this is the reason it works. I mean, it's the explanation as to why it works. Okay. Is this a suitable site? Okay. First of all, nobody can design a site from a GPS or any other of these databases that are available. You have to go out on the site and get the subtleties. I gather these...
Actually, Rodney, can I give a shout out here to... this is actually a location in the far northwest of Michigan. excuse me. And we do have a couple of representatives from the health jurisdiction for this area. And I'm just wondering if either of them have a built-in microphone. Would you let me know? If you do, would you turn it on, please? No, they don't have a microphone this morning. But I can give you a quick cook's tour of what you're looking at here. These are high bluffs overlooking Lake Michigan, and subsurface drip dispersal has been used successfully in this jurisdiction for some time because people buy property here because of the amazing views, the beautiful ridge lines, the amazing tree coverage. And you can see on this particular map here, let me go to my tool, the contour line there. Obviously, if you're trying to put a system in here, you really don't want to be taking down trees. So back to you.
Okay. Yeah, there's no reason. I mean, these GPS maps are very, very useful indeed. They can tell you where you can't put in a system, but they can never really tell you where you can put in a system. In other words, you need to go on site to look at the specific detail. But sometimes when they're going to show you that there's a wetland or a high water table, or it's obviously, when there's a big gully where the rain obviously comes pouring down, there's some areas that you must avoid. But typically, there's lots of systems all the way down the coast. Whether you start all the way down the Pacific coast for sure, where I live, starting in British Columbia, where we have a lot of systems in British Columbia and the islands of British Columbia, all the way down through Washington, Oregon, and California. Large number of systems along the coast. And again, because of the rapid absorption of the fecal coliforms from the drip system, if it's correctly designed, there's no limitation on the ability to handle slopes and wooded areas. There's no limitation on how to do it. So now again, they're showing the depth. They're showing the depth in feet. This area is 0 to 15, so that is this area is 0 to 15 feet here. But of course, that doesn't help us very much because if we've got 5 feet, we're probably more than okay. And of course, once you get up here, your water table depth is very deep. So again, there's no reason not to go ahead and check out the site. And this is a drawing of the site, and I gather the person who is involved in it is going to make some comments. But again, this is pretty typical.
Yeah, actually, Rodney, there's a message from Larry that his microphone isn't working, but please feel free, Larry or Scott, and I believe Dan Begnosh is there too, enter in the chat window any comments about this particular location. Actually, Rodney, if you want to just do a quick tour through what you're seeing there, that really is that's an actual as-built drawing of the subsurface drip dispersal system in the heavily sandy areas of northwest Michigan.
If we look at this, I mean, this is a septic tank, and then it's going straight to a dosing tank. So this is primary treated effluent. It's not secondary treated effluent, which is fine, as I said. As I said, it works. And that in turn is going into a headworks, which has got the filter, which is there, and then out through a supplier console, which is supplying, which is flush, which side, but it doesn't matter, up and through the drip system and back down the other side. And they've got air vacuum breakers here and here, so I presume the slope is going this way from the position of the air vacuum breakers. But it's exactly very, very similar to the previous drawings, and here they've got the air vacuum detail. And okay, is there any comments there?
No, but when we get to the end of the presentation, I'm assuming there are going to be some questions from regulators. We've talked a lot about how subsurface works, but I think this drawing really shows the things that people need to be looking at when they're going to be approving designs. So we can come back to this one later. But go ahead.
Yeah, I mean, considering this, I don't know really how cold it does get on the North Shore. I mean, yeah, I would obviously include insulating information here, because this is a standard drawing without the insulating material being shown. But it doesn't mean that he hasn't written down, that the designer hasn't written down the requirements for insulation, and I'd be a little concerned if this is the slope running this way, and there really is a slope running this way, that this will not drain back to the pump tank, which is higher. But again, I haven't got the contours, so there's no point. It might be a completely incorrect statement. Okay. This is an extract from Rachel Bora's dissertation. Okay, she took 2 ATU sites. Okay. The fecal coliform and E. coli concentrations were very low throughout the profile. Based on median values, fecal coliform concentrations were at or below detection limits at a depth greater than 2.5 centimeters below the drip line. So 1 inch below the drip line, the fecal coliform content was down to background level or undetectable. Now, the fecal coliform concentration of the influent was pretty low to start with, at 250 colonies per 100 milliliters. Now, in the design done before with septic tank effluent, we can probably add a 0 to that 250 colonies, or at least I don't know if anybody else can type in what you would expect the fecal coliform count of a septic tank. I don't offhand remember that number. But anyway, it will be considerably larger. And maybe it'll take more than 1 inch. Maybe it'll take 6 inches before we're down to the concentration level. Now, in her dissertation, she does deal with septic tank effluent, and she does deal with a lot more. But the fact is that, particularly with secondary treatment effluent, the treatment takes place very, very, very close, very, very close to the dripper. And so then the question of how far you need to be above the water table becomes a question of regulations, not a question of engineering. Now, tomorrow we're going to talk about soils to some degree. Now, as I said earlier, and there's not an accident, if any mistakes are made, when you as a regulator can catch them, must catch them, it is at the soils. It is the soils. These are mistakes if there's an error in the soils analysis and the soil study, and it's in the wrong direction. These are the failures that are very, very difficult and often impossible to fix. Anything else, as I said earlier on, you can usually somehow or other fix. Everything else is mechanical. But the soils, you can improve the treatment even if necessary. Even let's say you started with septic tank effluent. Let's take that system we had 2 slides before, which is septic tank effluent. Well, in this case, if there is a soils error, you could put in secondary treatment and that might save it. But if the area is too small, you could put in secondary treatment and save it. But if you've made a real design error with soils and you're already in secondary treatment, boy, you're in trouble. So that's why I stress that's the most important thing you can look at is the soil study. Okay, the reasons that we get failures with drip systems, the main reasons are poor site reviews. We have people, and I'm sure you have them, where the designers, well, maybe they slow their truck as they drive past the site before they go and design it, or maybe they don't even take their truck out of the garage. It's done. It's done. It's done from Google Maps, from Google Earth. I mean, what can I tell you? I mean, your regulators, I think you know this as well as I do. Poor soils and installation problems are the next problem. You get people taking shortcuts on installation. I had one system in a state park in the state of Washington in which the instructions were clear to the contractor that he had to prepare the soil. He had to, go down 6 inches below the surface. And he went and put the drip line on top of the surface. He did the native surface. He didn't work it at all. He put the drip line on top, put 6 inches of soil on top of that, and the next thing is the water was seeping from the drain field down onto the road below. Now, of course, he got caught. And but you get people doing this, and sometimes, it's very annoying, but again, your regulators, and this is what you live with. Incidentally, we managed to fix that quite easily by ploughing in between the lines, in between each line. There was 2 feet between lines, and we ripped up in between the lines, so as the water flowed down the slope, it flowed down into the ripped up area and percolated through into the soil below. But the contractor should be shot, or whatever penalties you have in Washington for that sort of thing. Poor maintenance, of course, is a standard problem. The system, if the treatment plant isn't maintained, if the filters aren't flushed, if the system isn't correctly flushed, it's a problem. I like 6 monthly, biannual. It's biannual every second year or every 6 months. Oh, well, anyway, every 6 months that somebody should go out, check the treatment plant and check the drip fields. Some states require that, some don't. Again, this is a regulatory issue, but if I had my way, everybody would require 6 months. But
Rodney, there was one question that related back to the design plan. So what considerations are necessary for primary treatment systems? Oh, and he just repeated that question, said if they are used for seasonal or intermittent use homes, i.e. lake cottages.
Yeah. Okay. All right. Yes. In a seasonal or intermittent use home, there's a lot of advantages in primary effluent. Because you don't have the stopped-up problem. Primary effluent, septic tanks fire up again and actually don't die to the same degree as, or you can keep them alive, artificially keep them alive, to a greater degree than ATUs or other secondary treatment equipment. So there's no question there is an advantage in using septic tank effluent under those circumstances. All right. You usually need a much larger area because of the fact you've got to have enough air in the soil. I recommend, and this is a personal recommendation, very few people accept it as being the way as being regulatory thing requirement, but I recommend going 12-inch by 12-inch on the drippers instead of 24 by 24. If you go 12-inch by 12-inch on the emitters, you use in the same area you have 4 times as many emitters. Okay, so the BOD, the biological loading per emitter, is cut by a factor of 4. So the risk of getting an anaerobic zone around that emitter is cut by a factor of 4. Now, if you also increase the area by, say, 50%, okay, you've now got 6 times as many emitters. So your BOD loading per emitter is now down to 1/6 of what it would be with a 2-foot by 2-foot spacing. And that would typically work. But if you have a heavy clay, I'm sorry, don't do it. I mean, or alternatively, if you have a heavy clay, you better have a huge area. To go back in history, septic and effluent started in Georgia. Back, oh, I don't know, let me say about 1990. About 1990, I guess. That's about 22 years ago. They started a septic tank effluent in Georgia. It wasn't with my company, but it doesn't matter. That's irrelevant for this discussion. And it was started in areas where conventional drain fields won't work, which of course is the horrendous clay in Georgia. And eventually those systems failed because eventually the anaerobic bacteria finally overpowered the soils, the air in the soils, and they failed like any conventional drain field will fail under those circumstances. But again, if you can pack in more drippers, increase the area, and you're going to be pretty well okay. There are anyway, there are, I'm sorry, I'm just trying to think. If you go to our design guidelines, you'll see we actually have our small system design guidelines, which will be applying in this case for the cottages, small single, summer use or winter use cottages. And we actually have a guideline on the area required according to the soil. But make sure you have a good soil scientist. And is that adequate? Drip lines are 1 foot centers, correct. And 12-inch between drippers, both. So you've got 4 times as many drippers as opposed to 2 foot by 2 foot. That's correct. And but as I say, it does work if it's designed correctly, but you have to just be very conscious and over-design. Don't under-engineer. Okay, this is, we're talking about houses along the coast. This is the Carmel Highlands, and the sea's right below here, and this is the drain field. Here's the Pacific, and here's the drain field. And this is fine. I mean, these systems work just fine. We've got a large number of systems in Malibu. Malibu doesn't have a central sewage system. Everything in Malibu's on a septic drain field one way or the other. And so we have a large number of drip systems in Malibu. And okay, so that gets the end of my presentation. And let's see what other questions we've got.
Yeah, thank you so much, Rodney. I do apologize if anyone had audio issues. We will try and get that resolved for tomorrow. But I'm going to open the floor up now for questions. If you would like to use your microphone, you may turn it on and speak, or forever hold your peace, as they say, or you can use the chat window. Does anyone have any specific design questions that they'd like to pose, or suggestions for increase in how to address this at a later time? I see a number of people in the chat window here. And just to assure you that Rodney's contact information, which I can pull up here in a little bit, will be posted with your let me just collect that here, and I'll post that into the chat window for you too. There's Rodney's contact information. Oh, there's some lengthy typings coming in here. Okay, here's one from Mary Clark. Mary Clark is with the state of Vermont, and she is also a wastewater education board member. And she commented that in some of the pictures that many of the lines and trenches don't actually look like they're on contour. Let's go back and pull one of those up. So it looks like there are sags and highs and low points. Is this an optical illusion, Rodney, or is this installation going in, they're just laying out the lines here? What's your take on that?
No, they certainly are not exactly on contour, but they're more than close enough. I mean, the drip line is full of holes, correct? And let's say that when you switch off, you get a little bit more water out of there because a little bit drains out. But the height difference here isn't going to set up a vacuum that's going to suck dirt back into the system. You see, the reason we want to be, there's two reasons not to be on contour. The main one is, if you get something
and there's
like this,
I'm sorry, go ahead.
When this drains, you can set up a vacuum here and suck dirt back into the drippers up here. So that's the main reason. Because you want, otherwise if you're like this, and as they drain, the air vacuum relief valve, which is up here, allows air to be drawn in fast enough to not to risk sucking dirt into the system. The other reason is, of course, you'll get more water here, but it's going to be very small if you've just got a small little sort of sack. But you don't want your drip line to be like this, because otherwise, with the manifold here and the manifold here, because then you'll certainly get more water here. But it's okay if it's like that, because then when you switch off, it'll drain that way and that way into the supply and flush manifolds. So you can live with that, you can't live with this. If this is too high, if you have something like that, then you might have to run another line across here from this clear and then put an air vacuum relief valve connecting them at the top, so that when you switch off, again you handle the vacuum set up as the lines drain that way and that way. So you connect all the laterals with another manifold and put an air vacuum relief valve at the top again.
And there's a question from Leslie, and Leslie logged out for a little while early on, but she's back in now, and she asks if you had talked about whether it was advisable to put a basin between ST and the pump tank. I'm trying to think if we had a slide for that one. Is it this one?
I can't see the question.
Yeah, it's 4 up from the bottom from Leslie Turner. Question whether
advisable to do the basin.
Yeah. By basin, Leslie, do you mean a pump chamber? No, between septic tank and the pump tank. Oh, between the septic tank and the pump.
The septic tank and the pump tank. What do you mean by a basin? My talk isn't on.
Okay. While Leslie's typing that in.
Okay. No, I don't understand the question.
Yeah. There's a question from Percy Johnson saying that in Missouri we allow a load rate for highly expansive clay soils at 0.1 to 0.05 gallons per day per square foot. Is this advisable considering the soil type?
Sorry, I'm taking a long time to think about that.
That's okay. Take your time, huh?
I presume this is secondary treated effluent.
Okay.
If it's secondary treated effluent, then make sure you have a good secondary treatment. I'd guess at 0.05 you should be okay. That's pretty low. I would hesitate at 0.1. Because, I mean, the water isn't going to move. I mean, and that's all there's to it. So, and when it's raining, it's certainly at the limit. I mean, there are soils that sometimes you just have to sort of say no. But, of course, if it's adequately treated, and you see, if you've got vegetation through the summer, it'll be fine. It's the winter that, of course, one has to be concerned about. And where's that water going to go to?
I think this was the illustration that that maybe Leslie missed. Okay, did you say it's advisable to have a basin for return that will flow into the pump tank to allow further settling?
Yes.
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 Okay.
I mean, if you're going to return to the pump tank, say you're returning to the pump tank like that, well, obviously it won't be like that, but the pump tank will be lower, it will be something like that. Then I'd suggest putting another settling basin in here, and then have the water come up into a settling basin and let it settle here, and as it overflows, then let it overflow gently into the pump tank. So you'll have minimum, so you'll have to pump this out. You'll start, that will build up here more rapidly, and it will prevent the dirt building up here. So you'll build it up here, which will be easier to clean out. In fact, you might even be able to, if you set it up correctly, you might even be able to drain it out or just pump it out. But
okay, I am going to remove, I'll just remove my smiley face from this one, which was designed to indicate happy bacteria settling into there in the slow times. But we are little over time, but if there are any more questions, by all means go ahead. If not, I think I'd like to thank Rodney for part one. We encourage you, same time, same place tomorrow at 11:15. Please log in a little bit earlier, and we're going to have work with Rodney and see if we can clear up some of his microphone issues, but hopefully the recording sounds fine on my end. So if you did miss any of the audio, please just log back in and listen to it through the link we're going to give you. Moving on here, this is our closing slide. Obviously, you will find us just about anywhere on the web: Facebook, Twitter, LinkedIn, YouTube, and now on Pinterest. We do encourage you to pin your favorite photos under our headings of wastewater systems we have known and loved, and regulators that we know and love. Just to remind all of you that we are very appreciative to Geoflow, who have underwritten most of the cost of this presentation so that we can offer it to regulators at no cost. We know an awful lot of you, and we know that your budgets are just as strained as they are here in Michigan. We do appreciate support for our organization. We are a nonprofit, and we rely upon donations and grants to continue our work, and we are an impartial entity that really is designed to do what our mission says: to increase awareness, to make education available, and increase people's access to that. I'm going to put in the window here, but again, we will be sending this out to you. Several of you had asked if there were going to be a handout with high-resolution images of the slides, and yes, there will. There is the link. We posted it to our Google Docs drive. If you have any issues at all getting in there and getting that document, just let me know. And with that, I am going to stop the recording, and we will see you again tomorrow. We will be hanging around in the room for a little bit, so if you have more questions or you want to experiment with your video cameras, do let us know. And thank you for your attendance. We will see you tomorrow.